Hello, I'm Sarah, and I'm here to guide you through the mind-bending math trick that changes everything. In mathematics, the Poincaré lemma gives a sufficient condition for a closed differential form to be exact, while an exact form is necessarily closed. Precisely, it states that every closed p-form on an open ball in Rn is exact for p with. The lemma was introduced by Henri Poincaré in 1886. Now, let's delve into a more relaxed exploration of the concepts presented. Especially in calculus. The Poincaré lemma also says that every closed one-form on a simply connected open subset in Rn is exact. In simpler terms, it means that if a differential form is closed in a region that can be shrunk to a point, then it can be written as the derivative of another form. That is, if d alpha equals 0 on a simply connected region, we can always find alpha equal d beta. Therefore, we have d beta equals 0, expressed simply as d2 equals 0. This concept is used in mathematical physics, particularly in the context of electromagnetism and differential geometry, where it relates to the fact that the boundary of a boundary is always empty. That is, if you have a surface, a 2-form, and you take its boundary, a 1-form, a curve, then the boundary of that boundary, a 0-form, a point, is an empty set. In electromagnetism, magnetic fields can be described using a vector potential, and the Poincaré lemma helps in finding such potentials when the magnetic field is well-behaved, i.e., when the magnetic field is not due to a monopole. Gauss's law for magnetism states that the total magnetic flux through a closed surface is always 0, which implies that magnetic monopoles, if they exist, are not isolated, but must be accompanied by other magnetic charges. In the language of cohomology, the Poincaré lemma says that the Kth-Durham cohomology group of a contractible open subset of a manifold M, e.g., M equals Rn, vanishes for k greater or equal to 1. In particular, it implies that the Durham complex yields a resolution of the constant sheaf Rm on M. The singular cohomology of a contractible space vanishes in positive degree, but the Poincaré lemma does not follow from this, since the fact that the singular cohomology of a manifold can be computed as the Durham cohomology of it, that is, the Durham theorem, relies on the Poincaré lemma. It does, however, mean that it is enough to prove the Poincaré lemma for open balls. The version for contractible manifolds then follows from the topological consideration. The Poincaré lemma is also a special case of the homotopy invariance of Durham cohomology. In fact, it is common to establish the lemma by showing the homotopy invariance, or at least a version of it. Prepare to have your perception of reality challenged as we delve into the fascinating world of mathematical illusions. A standard proof of the Poincaré lemma uses the homotopy invariance formula, cf. See the proofs below, as well as integration along fibers number example. The local form of the homotopy operator is described in, and the connection of the lemma with the Morichartan form is explained in. Dive into the fascinating world of mathematical rigor with direct proof. The Poincaré lemma can be proved by means of integration along fibers. This approach is a straightforward generalization of constructing a primitive function by means of integration in calculus. We shall prove the lemma for an open subset Urn that is star-shaped or a cone over, i.e., if x is in U, then Tx is in U for 0 less or equal to T less or equal to 1. This case in particular covers the open ball case, since an open ball can be assumed to be centered at the origin without loss of generality. The trick is to consider differential forms on U times Rn plus 1. We use T for the coordinate on. First, define the operator pi, called the fiber integration for k forms on U times by pi sum sign I1 ik minus 1. Fi dt dxi plus sum sign j1 jk gj dxj equals I1 ik minus 1. Integral fi t dt dxi where dxi equals dxi1 dxik minus 1. Fi equals fi1 ik minus 1. And similarly for dxj and gj. Now for alpha equals f dt dxi, since $d alpha equals sum L frac, partial f, partial xl dt wedge dx L wedge dxi dollar. Using the differentiation under the integral sign, we have pi d alpha equals alpha 1 minus alpha 0 minus d pi alpha, where alpha 0, alpha 1 denote the restrictions of alpha to the hyperplanes t equals 0, t equals 1 and they are 0 since dt is 0 there. If alpha equals g dx j, then a similar computation gives pi d alpha equals alpha 1 minus alpha 0 minus d pi alpha. Thus, the above formula holds for any k-form alpha on u times. The formula is a special case of a formula, sometimes called the relative Stokes formula. Finally, let hx, t equals tx and then set j equals pi h. Then, with the notation ht equals ht, we get, for any k-form omega on u, h1 omega minus h0, omega equals jd omega plus dj omega, the formula known as the homotopy formula. The operator j is called the homotopy operator, also called a chain homotopy. Now if omega is closed, jd omega equals 0. On the other hand, h1 omega equals omega and h0 omega equals 0, the latter because there is no non-zero higher form at a point. Hence, omega equals dj omega, which proves the Poincaré lemma. The same proof in fact shows the Poincaré lemma for any contractible open subset U of a manifold. Indeed, given such a U, we have the homotopy ht, with h1 equals the identity and h0 u equals a point. Approximating such ht, we can assume ht is in fact smooth. The fiber integration pi is also defined for pi, u times right arrow u, hence the same argument goes through. Prepare to delve into the rigorous mathematical foundation behind this astonishing illusion. Cartan's magic formula for Lie derivatives can be used to give a short proof of the Poincaré lemma. The formula states that the Lie derivative along a vector field xi is given as L xi equals d I xi plus I xi d, where I xi denotes the interior product, id I xi omega equals omega xi. Let ft, u right arrow u be a smooth family of smooth maps for some open subset U of Rn, such that ft is defined for t in some closed interval I and ft is a diffeomorphism for t in the interior of I. Let xi t, x denote the tangent vectors to the curve ft, x, id $frac ddt ft x equals xi t ft x $. For a fixed t in the interior of I, let gs equals ft plus s, ft. Then $g0 equals operator name id, frac ddsgs, s equals 0, equals xi t $. Thus, by the definition of a Lie derivative, $L xi t omega, ftx, equals frac dds gs omega ftx, s equals 0 equals frac dds, ft plus s omega x, s equals 0 equals frac ddt, ft omega x $. That is, $frac ddt, ft omega equal ftl xi t omega, $assume I equals. Then, integrating both sides of the above, and then using Cartan's formula and the differentiation under the integral sign, we get, for 0 t0 t11, ft1, omega minus ft0, omega equals d integral t0, t1 ft, I xi t, omega dt plus integral t0, t1 ft, I xi t, d omega dt, where the integration means the integration of each coefficient in a differential form. Letting t0, t1 right arrow 0, 1, we then have f1 omega minus f0, omega equals dj omega plus jd omega, with the notation j omega equals integral ft, I xi t, omega dt. Now assume U is an open ball with center x0, then we can take ft, x equals t, x minus x0 plus x. Then the above formula becomes omega equals dj omega plus jd omega, which proves the Poincaré lemma when omega is closed. Prepare to have your perception of reality challenged as we delve into a deceptively simple mathematical concept. In 2 dimensions, the Poincaré lemma can be proved directly for closed one forms and two forms as follows. If is a closed one form on then, if then and set gxy equals integral a x pt y dt, so that then must satisfy and. The right-hand side here is independent of x since its partial derivative with respect to x is q x minus p y equals 0. Since q minus delta g slash delta y is independent of x, it is a function of y only. To find this function, we can evaluate it at any arbitrary value of x, specifically at the boundary x equals a. hxy equals integral c, yqas ds minus g a y equals integral c, yqas ds. And hence, fxy equals integral a x pt y dt plus integral c, yqas ds. Similarly, if then with Thus a solution is given by and bxy equals integral a x r t y dt. Prepare to explore the fascinating world of mathematical reasoning with the next section. Inductive proof. It is also possible to give an inductive proof of Poincaré's lemma, which does not use homotopical arguments. Let xm equals im, where I equals -1, 1, be an meters dimensional open coordinate cube. For each n less or equal to m, the projection pi mn. Xm right arrow xn, which deletes the last mn coordinates of a point, is a fibration, and therefore the pullback map pi m n. Omega xn right arrow omega xm is a monomorphism. We may thus consider any differential k-form which is defined on xn to be also defined on xm with no additional notation. Conversely, a k-form omega omega k xm descends to a necessarily unique k-form on xn if and only if its expression with respect to the standard coordinates is omega equals 0 less or equal to I1, ik less or equal to ng omega I1, ik x1, xn, dx I1, dx ik. Or in other words, its coefficients are functions of the variables x1, xn only, and differentials of only the latter variables are involved. For a differential k-form omega omega k xm, let its codegree be the integer mk. The induction is performed over the codegree of the form. Since we are working over a coordinate domain, partial derivatives and also integrals with respect to the coordinates can be applied to a form itself by applying them to the coefficients of the form with respect to the canonical coordinates. First, let omega omega m xm, that is, the codegree is 0. It can be written as omega equals dxm, omega 0 equals f x1. xm dx1 dx m-1. So if we define theta omega m-1 xm by theta equals integral xm omega 0 x1 xm-1 s ds, we have theta equals dxm delta m theta equals dxm omega 0 equals omega. Hence, theta is a primitive of omega. Let now omega omega k xm, where 0 km, that is omega, has codegree mk, and let us suppose that whenever a closed form has codegree less than mk, the form is exact. The form omega can be decomposed as omega equals dxm, omega 0 plus omega 1, where neither omega 0 nor omega 1 contain any factor of dxm. Define lambda equals integral xm omega 0 x1 xm-1 s ds, then d lambda equals dxm omega 0 plus lambda 1, where lambda 1 does not contain any factor of dxm, hence defining omega equals omega minus d lambda equals omega 1 minus lambda 1. This form is also closed, but does not involve any factor of dxm. Since this form is closed, we have 0 equals d omega equals dxm delta m omega plus omega, where the last term does not contain a factor of dxm. Due to linear independence of the coordinate differentials, this equation implies that omega equals 1 less or equal to I1, ik less or equal to m-1, omega I1, ik x1, xm-1, dx I1, dx ik, i.e. the form omega is a differential form in the variables x1, xm-1 only, hence it descends to an element of omega k xm-1, and its codegree is thus mk-1. The induction hypothesis applies, thus omega equals d theta for some theta is omega k-1, xm-1 omega k-1, xm, therefore omega equals d theta, theta equals theta, plus lambda, concluding the proof for a coordinate cube. In any manifold, every point has a neighborhood which is diffeomorphic to a coordinate cube. The proof also implies that on a manifold any closed k-form, for 0 k less or equal to m equals dim m, is locally exact. Fascinating illusion reveals a surprising connection to fundamental mathematical concepts. By definition, the kth de Rham cohomology group HDR K U of an open subset U of a manifold M is defined as the quotient vector space. HDR K U equals closed k-forms on U / exact k-forms on U. Hence, the conclusion of the Poincaré lemma is precisely that if U is an open ball, then HDR K U equals 0 for k greater or equal to 1. Now, differential forms determine a Cauchy complex called the de Rham complex. $omega 0 to omega 0 over set d0 to omega 1 over set d1 to c dots to omega n to 0 where n equal the dimension of m and omega. K denotes the sheaf of differential k-forms, i.e. omega k. U consists of k-forms on U for each open subset U of M. It then gives rise to the complex, the augmented complex. $0 to math bar M over set. Epsilon to omega 0 over set D0, to omega 1 over set D1, to c dots to omega n to 0 where Rm is the constant sheaf with values in R, i.e., it is the sheaf of locally constant real-valued functions, and letter 3F5 the inclusion. The kernel of D0 is Rm, since the smooth functions with zero derivatives are locally constant. Also, a sequence of sheaves is exact if and only if it is so locally. The Poincaré lemma thus says the rest of the sequence is exact too, since a manifold is locally diffeomorphic to an open subset of Rn, and then each point has an open ball as a neighborhood. In the language of homological algebra, it means that the de Rham complex determines a resolution of the constant sheaf Rm. This then implies the de Rham theorem, i.e., the de Rham cohomology of a manifold coincides with the singular cohomology of it. In short, because the singular cohomology can be viewed as a sheaf cohomology. Once one knows the de Rham theorem, the conclusion of the Poincaré lemma can then be obtained purely topologically. For example, it implies a version of the Poincaré lemma for contractible or simply connected open sets. See section Simply Connected Case. Prepare yourself for a deceptively simple demonstration. Especially in calculus, the Poincaré lemma is stated for a simply connected open subset U(Rn). In that case, the lemma says that each closed one-form on U is exact. This version can be seen using algebraic topology as follows. The rational Hurwick's theorem, or rather the real analog of that, says that H1U R equals 0 since U is simply connected. Since R is a field, the kth cohomology HK, U, R is the dual vector space of the kth homology HK, U. R, in particular, H1U, R equals 0. By the de Rham theorem, which follows from the Poincaré lemma for open balls, H1U, R is the same as the first de Rham cohomology group, see section Implication to de Rham cohomology. Hence, each closed one-form on U is exact. Let's delve into Poincaré lemma with compact support. There is a version of Poincaré lemma for compactly supported differential forms. The usual proof in the non-compact case does not go through since the homotopy H is not proper. Thus, somehow a different argument is needed for the compact case. Prepare to explore a surprising connection between seemingly disparate mathematical concepts. On complex manifolds, the use of the Dalbolt operators delta and $bar partial dollar for complex differential forms, which refine the exterior derivative by the formula $d equals partial plus bar partial dollar, lead to the notion of $bar partial dollar closed and $bar partial dollar exact differential forms. The local exactness result for such closed forms is known as the Dalbolt-Grothendieck lemma or $bar partial dollar Poincaré lemma. Cf. Importantly, the geometry of the domain on which a $bar partial dollar closed differential form is $bar partial dollar exact is more restricted than for the Poincaré lemma. Since the proof of the Dalbolt-Grothendieck lemma holds on a polydisk, a product of disks in the complex plane, on which the multidimensional Cauchy's integral formula may be applied, and there exist counterexamples to the lemma even on contractible domains. The $bar partial dollar Poincaré lemma holds in more generality for pseudo-convex domains. Using both the Poincaré lemma and the $bar partial dollar Poincaré lemma, a refined local $bar partial dollar Poincaré lemma can be proven, which is valid on domains upon which both the aforementioned lemmas are applicable. This lemma states that declosed complex differential forms are actually locally $bar partial dollar exact, rather than just d or $bar partial dollar exact, as implied by the above lemmas. Prepare to delve into the surprising connections between geometry and physics. The relative Poincaré lemma generalizes Poincaré lemma from a point to a submanifold, or some more general locally closed subset. It states, let V be a submanifold of a manifold M and U, a tubular neighborhood of V if sigma is a closed K-form on U, K greater or equal to 1, that vanishes on V. Then there exists a K-1 form eta on U such that d eta equals sigma, and eta vanishes on V. The relative Poincaré lemma can be proved in the same way the original Poincaré lemma is proved. Indeed, since U is a tubular neighborhood, there is a smooth, strong deformation retract from U to V, i.e., there is a smooth homotopy HT. U right arrow U from the projection U right arrow V to the identity such that HT is the identity on V, then we have the homotopy formula on U. H1 minus H0 equals dj plus jd, where j is the homotopy operator given by either Lie derivatives or integration along fibers. Now H0, UV and so H0, sigma equals 0. Since d sigma equals 0 and H1, sigma equals sigma, we get sigma equals dj sigma, take eta equals j sigma. That eta vanishes on V follows from the definition of j, and the fact HT, V, so the proof actually goes through if U is not a tubular neighborhood, but if U deformation retracts to V with homotopy relative to V, white small square. Prepare to delve into the fascinating world of polynomial differential forms. In characteristic 0, the following Poincaré lemma holds for polynomial differential forms. Let K be a field of characteristic 0, R equals K the polynomial ring, and omega 1 the vector space with a basis written as dx1, dxn. Then let omega p equals p omega 1 be the pth exterior power of omega 1 over R, then the sequence of vector spaces. $0 to K to omega 0 over set D, to omega 1 over set D, to C dots to $0 is exact, where the differential D is defined by the usual way, i.e., the linearity and $df dx I wedge C dots wedge dx IP equals sum j frac partial f dxj dxj wedge dx I wedge C dots wedge dx IP $. This version of the lemma is seen by a calculus-like argument. First note that cur d, R right arrow omega 1 equals K clearly. Thus, we only need to check the exactness at P0. Let omega be a P form. Then we write omega equals omega 0, dx1 plus omega 1 where the omega i's do not involve dx. Define the integration in x1 by the linearity, and $int x1r dx1 equals frac x1r plus 1r plus 1, which is well defined by the char 0 assumption. Then let eta equals integral omega 0 dx1, where the integration is applied to each coefficient in omega 0. Clearly, the fundamental theorem of calculus holds in our formal setup, and thus we get d eta equals omega dx1 plus sigma, where sigma does not involve dx1. Hence, omega minus d eta does not involve dx. Replacing omega by omega minus d eta, we can thus assume omega does not involve dx. From the assumption d omega equals 0, it easily follows that each coefficient in omega is independent of x1, i.e., omega is a polynomial differential form in the variables x2, xn. Hence, we are done by induction, white small square. Remark, with the same proof, the same results hold when R equals K is the ring of formal power series or the ring of germs of holomorphic functions. A suitably modified proof also shows the $bar partial $Poincaré lemma. Namely, the use of the fundamental theorem of calculus is replaced by Cauchy's integral formula. The Poincaré lemma generally fails for singular spaces. For example, if one considers algebraic differential forms on a complex algebraic variety in the Zariski topology, the lemma is not true for those differential forms. One way to resolve this is to use formal forms, and the resulting algebraic de Rham cohomology can compute a singular cohomology. However, the variants of the lemma still likely hold for some singular spaces. Precise formulation and proof depend on the definitions of such spaces and non-smooth differential forms on them. For example, Kontsevich and Soibelman claim the lemma holds for certain variants of different forms, called PA forms, on their piecewise algebraic spaces. The homotopy invariance fails for intersection cohomology. In particular, the Poincaré lemma fails for such cohomology. Prepare to have your perception of mathematics fundamentally altered by this incredible discovery.